SF Systems Club? I don't know. Let's do a quick show of hands. How many people have been to one of these? I guess, implicitly, 2 of these? 3 of these? 4 of these? Have we held 5? I don't know. But if you've been to all of them, thank you for coming. This one is a very, very special one because we have some interesting speakers that you'll hear about. But I'll give a quick overview of what we want to do with this. So at the SF Systems Club, we want to form a community that brings together both researchers and people in industry. And these talks try to focus on core engineering without a lot of marketing or product fluff. We just want to get to the details. So the team, about several people. Chris Wenzel, right over here. We have Connor Power. We have Jeff Huber, somewhere, maybe. Me, Neil. That is out of date, OpenAI now. And Shadaj, who was back there.
It's his first day.
It is my first day at OpenAI, yes. Thank you. And you can scan this QR code for subsequent events. And with that, I will hand it off to Shadaj.
Thank you, Neil.
There you go.
All right, I'll go back to the previous slide real quick. All right, so one of the things that we're looking for is new speakers for our future meetups. I think, if you are working on any cool projects in the system space, and, we really consider systems to be a really wide area. So compilers, working on distributed systems, databases, security, networking, all sorts of stuff. If you've been working on a cool project, we really encourage you to just send over an abstract of what you've been working on and sign up to give either a lightning talk or a full-length half-an-hour talk. And you can always sign up at bit.ly/sfsystemstalk. And speaking of, more talks, we're planning to have our next meetup in July, sometime after the 4th of July holiday. We are actively looking for a space to host the next meetup. I say this at every single meetup. We're looking for spaces with roughly 150 capacity or higher. So if you have a space that might be able to host, please reach out. All of us are around, and you can grab any of us. All right. So before we get started with today's talks, we'd like to give a big shout out to OpenAI, our host for today, and Ben will share a little bit about what OpenAI does.
Hi, everybody. We're a model provider. Thank you for coming. A couple quick notes about the space. We have this space and the space out there. We have them after talks too. Please eat food, please drink drinks. We have non-alcoholic beer as well. I have to shamelessly recruit for literally 1 minute, so just give me this 1 minute. Brian, can you raise your hand? Brian? This is Brian. Brian is a recruiter for infrastructure at OpenAI, so if you want to work at OpenAI, talk to Brian. Everyone else who works at OpenAI, can you raise your hands? These people work at OpenAI. We're not going to shamelessly recruit, but if you're curious what things are like, talk to them. And then talk to Brian, because you're going to want to apply, right? That's pretty much it. I work on the infrastructure at OpenAI. I'm on the reliability team. We work on chaos testing, load testing, networking, config delivery, lots of things. So if you're curious about any of that or the big outages we've had lately, talk to me. And with that, I will hand it back to hosts, right? Yeah. Here's Connor.
Hey, I'm Connor. I'm just here to introduce the speakers. So without further ado, our first speaker is going to be Brian Lagoda from Antithesis, and he's going to be telling us about what Mega Man can teach us about fuzz testing. There'll be time for questions after this talk.
Get a slide set.
Should I try to figure out how to attach this mic to me while you do that?
Yeah, it's done, so it'll be cool.
Oh, shit. Is that hanging out? Is the recording mic working? Cool. Sure. Awesome. And do we have my speaker notes somewhere? Oh, will they? Doesn't look like it. I can probably freehand it, but I would Can we take a sec? I'm totally mirrored. Is that what we're expecting? Like, oh, no, this looks right. Okay.
Yeah, that's working. Okay, great.
Great. Cool. Amazing. Yeah, right. Where are those? Is that another window? Shit. Sorry, guys. Great. Yeah. I'm not going to get those two objects, which is a shame because those are videos. So sorry about that. Didn't think about it. Cool. So what's up, everybody? My name is Brian. I work at a company called Antithesis. For those of you who don't know, we're an autonomous software testing company. Other companies send us their applications. We spin them up in our environment and explore what sorts of states we can twist them into so that we can find the bugs in them. Along the way to pulling that off, we built I should hang on to this, shouldn't I? I'm being inconsistent. Along the way to pulling that off, we've built an intelligent fuzzer to explore various software. And instead of talking about finding bugs or the various ways we can apply this to modern software, I'm going to talk about the other thing that everybody does whenever they have a powerful enough program on their side, which is using that thing to play a video game. Wait, am I not? The slides don't advance now? Does it? Cool, okay. Quick show of hands. Is everybody here familiar with fuzzing? Okay, that's more than half the room, but not everybody. So we'll do a quick recap. Fuzzing is a form of automated testing where you look for bugs in software by feeding it random inputs, right? At its very dumbest, it's basically a brute force search over inputs, but we don't have to stay at the very dumbest. And if we're going to make progress in a video game, we're going to have to get smarter than that. But what sorts of things do people normally fuzz? Does anybody want to shout out the sort of stereotypical fuzzer targets? Yeah, parsers, compilers, languages, right? Fuzzers are at their sweet spot when you're dealing with something that is responding to its input and nothing else, right? So if you feed it random input, you will actually be working your way through the set of things it can do. And most importantly, if you send it the same input twice, it'll do the same thing each time, right? We want something that is functional and stateless over its inputs. And that's sort of the happy place for fuzzing. So parsers are great, codecs are great, anything like the, security people love those sorts of things where you take, untrusted inputs over the wire and make some decisions about it. Great places to find bugs. Antithesis has built some tooling for letting stateful or network-oriented or multi-process or all of these things that you can't fuzz run in our system, and we can still fuzz over it. But I won't need to take advantage of any of that today because we're going to be working on something that is functional and stateless, the original Nintendo. I feel like, the first question here is what do you mean the Nintendo is stateless? We push buttons, the guy moves, he's over there now. Isn't that state? But when you look at what's actually going on in the console, right, there's no clock, it's single process, it's, there's no hard drive, there's no storage at all, there's nothing that can create these sorts of changes. There's just the inputs coming from the controllers. So if we imagine each controller state as an input, we can build that up as a functional input to the program, right? And so if you pick some moment of, I've been playing this game for a few minutes, and you look at every set of buttons you pressed along the way for every frame, you now have a function over that input. The game is stateless from power on to wherever you got. And so because the game is stateless, we can now just naively fuzz it. We can say, turn it on, generate some bytes, feed the bytes into the game, and see where it gets. And this, if I had been paying attention, would have been a video of exactly how much Mega Man you play over there.
Reload the page, I think we fixed it.
Really? Oh man, I figured it was my fault. Nope, still me. If I send this to me, will I get it so fast I can do it live? We are gonna learn something. Oh, totally did. Totally did. Cool. Yes, I know Ben is not an antithesis, but he's cool, so it's fine. Awesome. Is that one gonna work? It's not even that good a video. Cool. So, yes, I know. No, don't have. So these sets of inputs, right? Each one of these, each button is a bit in the byte. This sequence of bytes will play through, the level for 20 seconds, and sometimes it's lagging. Sometimes the game is just very slow because it's the Nintendo. But this is exactly the sort of input that we're going to be creating with our fuzzer, and this is what it looks like when one of them is played. And you can actually feed this into a real Nintendo. People make an adapter where you can run it from your computer and it'll send the little signals. It's totally real. Okay, lost some time. Gonna try and go a little bit quicker. Who here are people familiar with Mega Man? Okay, a little bit. So Mega Man is like the Dark Souls of Mario. It's a super punishing 2D platformer. You run, you jump, you shoot. There are a lot of guys that want to kill you. You've got a health bar. Like at the end of each level, there's a boss fight. Sort of, high on the list for the Nintendo Hard Wikipedia page. Just absolutely punishing game for humans, but still great. But can be fun, and we can throw our fuzzer at it. So, how far do people think we're going to make it if we, lost the next video, great. How far do people think we're going to make it if we, start fuzzing Mega Man? Whatever, get there later. 100%. Yeah, that'd be great. So we're gonna run it for a little while, right? We'll run it for like a day of human time, which is maybe 1,000 compute hours, and we will get a map like. Cool. And we'll get a map like this one. So this is everywhere that we have made it to in one of the levels of Mega Man in 20 hours of fuzzing with random inputs. Anybody want to guess how much of the game this represents? It is this much. We don't make it out of this first room. We bumble around in there. We, bounce off the ceiling. We grab onto the ladder. We get absolutely, beaten to death by that guy with a terrible grin. And eventually we die. We start over. We land, at the beginning of one of the levels. And that's it. 20 hours, and we don't make it out of sight of the start screen. We make it a little bit out of here. You can't quite see it with the sun the way it is, but if you squint a little bit, you can see a couple of dots outside of our little starting jail where we made it over. So we know that the problem isn't that we literally can't button mash our way out of there, right? Like there is some combination of buttons that that wasn't a criticism. I'm so sorry. The sun is going away now. We know that we can mash the buttons into a combination that will actually get us out of there. It's just that each thing adds up exponentially, right? First, you need to, make it to the left and get onto the ladder, and then you need to hop over the little box, and then you need to hop over the next little platform. And each one of these things adds up over time, right? And so even though mechanically we can mash our way into them, each one along the way is trying to throw us off. We have all of these places where we can lose ourselves, and that is the thing that we are going to be attacking when we try to beat Mega Man. So what can we do about this, right? So, please, yes, cool. So Black box fuzzing is what we were doing a minute ago, is basically throwing inputs at a program and not paying any attention at all to what the program is doing. So the most naive thing that we can do is pay literally any attention to what the program is doing. So we've got some pseudocode up here that's a little bit what we want to do with each frame of Mega Man as it comes in, and what we want to do in the future, right? So those are the two core functions here. Suggest frame says, when I want to generate new inputs, where should I start from? I could start from somewhere other than power on, because remember, everything up to where I am got me here deterministically, so I can just append to the end of that. And observe frame, I'm going to run on every frame as it goes by, and I can decide maybe I want to hang on to something, right? In classic fuzzing, the way that you would do this is with something like code coverage. You'd see which blocks you've activated, you'd see which functions you're running for the first time, you'd try to catch a bunch of different orderings of things, or even just maximize the amount. This works terribly for the Nintendo because it boots everything up immediately, runs almost all of its routines, it gets started and starts ticking, and so you pick up almost all of your code edges in the very beginning. But on the other hand, the working memory of the thing is 2 kilobytes. So we can just look at literally every memory address point that the game points at and grab the fun ones. So up here, we're grabbing a memory address that is what screen are you on in the level, and a memory address that is what is your X position on the screen. And if you add those things together, you can get an X value for where Mega Man is in the game. The levels pretend with fancy scrolling tricks to go up and down and whatever. They're totally linear. It's just screen, 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 screen. And so we can flatten them out, and we can say, what we want to do here is grab the frame where we are the furthest to the right. And so if a new frame comes in and it is further right than the thing that we're currently hanging on to, we replace the thing we have, and the next time we go to grab something, we'll return that. Cool. So a little bit smarter, can lock in our gains, ready to maximize how far right we are. How far do we make it in the game? We make it about twice as far. I wanted to just lead with a screenshot here, but thanks to old Nintendo graphics, the screenshot looked literally identical because we've got 2 rooms back to back. But you can see the new heat map. We are making it out of there, and we're making it further on, but we're getting stuck in almost the same position we were before. It's a little bit tougher than it was last time. You don't see it here, but there are now 3 little guys harassing you over there. But the general problem is that our hanging on to things hasn't quite worked for us. We're getting stuck. There's something wrong. It feels like if we had gotten lucky, if we had made it, a different route, maybe we had gone over top, we could have kept going. But it's much easier to go on the bottom, and so we get trapped in this local maximum X state. And so in general, right, when we find ourselves feeling like we've gotten unlucky, that's a sign that there is some hidden state, something about the program that we're working on that we haven't accounted for. The smarter our fuzzer is, the more dangerous this kind of a trap is, right? If you're starting with a totally black box system, you're totally, you don't have to worry about any of it. If you've got something that's overwhelmingly random, you won't tend to get stuck in forever pits. But the more opinionated the fuzzer is, the more you're trying to hang on, the more you're trying to figure out what's going on in the system I'm testing, the more likely you are and the more dangerous it is to get to a pathological state where you have thrown out some important piece of information and you are throwing all of your exploration at a dead end. So I like the term convergence to talk about the sort of fuzzing configuration where you are likely to see the same kinds of things every time you run it instead of getting lucky and unlucky. And so I'll use convergence and non-convergence a little bit today to talk about that. And so this is a little bit bad convergent, but kind of non-convergent, right? If you ever made it over the top in some run, that run would behave completely differently than the 90% of runs that get stuck here. So how do we deal with it? So we've got, with a little piece of obvious secret state, like Mega Man's Y position, right? That's the thing that we were missing in the old configuration. We might just be able to integrate it. But we also, now that we've noticed that we're, not convergent in the first place, we could reimagine the way that we're proposing places to start to be more convergent, like from the get-go. So instead of hanging on to one frame that could be, our checkpoint, now let's keep a map of them. And instead of hanging on to just the X, we can grab the X and Y. But we don't want to get every pixel of X and Y because then we're back to the explosive set of possibilities that mean we're, not actually winnowing down our search space at all. So some kind of a compromise here, I'm grabbing 32 pixel blocks. It's something like 8 by 9 or I forget how the numbers work out exactly. And we're saying for every block in the game, every time we land there, we should put that in our list, and we can randomly pick that to deploy from. So now, instead of saying get all the way to the right, we're saying go everywhere, explore every state you can reach. So how's that doing? How are we doing now? This is a little bit trickier. It doesn't have the same behavior we had before, where we just like plow into a wall, right? At 20 hours, what we're seeing is not that we're stopped. We're not stuck. We're just slowing to a crawl. The deeper we get, we are getting exponentially worse at making further progress. That feels a little bit different than the kinds of missing state we had before, but there's still something up, right? And maybe if you guys compare these two screenshots, you can tell what it is. So what we see here, right, we've got two bars on the left. One of them is Mega Man's item. The other one is his health. Over time, if you're not paying any attention, it's very natural for his health to go down because everything is trying to kill him. And eventually what will happen is that he will just get to a place where every grid square we have is a place where he is almost dead. And then if he wants to make any progress at all, he has to play perfectly. It's possible to do. Humans do it. I couldn't. But some people can actually play. So you never get to a place where it's stuck. It just gets worse and worse and worse. And so what do we do with that, right? We're in the same kind of situation we were before, where there's a piece of hidden state that we want to account for, but we definitely can't make this into a grid dimension, right? That would absolutely explode too far, and we don't really want it, right? We, want to see some places where he's low and some places where he's high, but we're not trying to hit every one. There's no place where it's like, you can only get through here if you have 14 health or whatever. So what we're going to do instead is we're going to use the health value as a way to optimize, right? So we've added our compare frames function, and instead of saying, instead of just taking the first frame where Mega Man is in some square, we'll take the highest health we've seen so far. And so what that means is that, if you make it back somewhere, however your road was there, with more health, we'll hang on to it, and it'll percolate through. This gets us way better performance on, the tricky areas where it's nice to take some hits because your health goes up. But you also get some really fun emergent behaviors at this point. This is where you'll actually see it start to farm health, because it'll, wander back into a health pickup and then scroll the screen, and, the whole path over there, it's replacing all the squares with higher health squares. And eventually it'll wander back, and the power-ups will have respawned when it scrolled off the screen, and it'll just keep doing that until it maxes its health out. Not always super helpful, really, really funny. So now we're not dying. We're exploring every square. And you can actually use basically that same trick to fight bosses, by the way. Instead of saying, I want my health to go up, you can say, I want the boss's health to go down. I want to explore every square in the boss room with the lowest boss health possible. And so, it's button mashing around, and eventually, finds states where the boss's health is lower and lower and lower as, it mashes the shoot button and they eventually connect. And eventually the boss is dead. So what about now? Have we beaten it yet? Like, you guys just heard me talk about killing bosses. Like, surely we're almost there. This one is actually the most annoying place. So sometimes for most of the levels, we will blow through absolutely immediately. This is, we've been looking at the Cutman level. This is the Gutsman level. So most of the half the time, you turn it on, it shoots through the Gutsman level and starts fighting the boss in like 25 minutes of human time. But about half the time, it gets stuck here and sits here for hours and hours and hours. What is happening, right? So we know because, I'm talking about differences between runs. We're getting unlucky. We know there's some kind of hidden state coming for us. But what is it? What are we missing? Oh, thank goodness this one's not a video. So in this little GIF, you can see what's going on with these platforms, right? They're going left and right. They'll run all the way from the left side of the track to the right side of the track, and every time they come over one of these little gaps, it drops off, and you have to successfully make a jump to wherever it's going to land. So if we look back at our heat map, we can see that when we're stuck, we are basically totally stuck on the left side of this little track. And so, what's going on? What's our secret state here? Turns out when we zoom in, what we end up with is Mega Man, where is Mega Man and where are these platforms in relation to each other when you hit the second row? So if you catch it, when the platform is on the left, going to the left, what happens is it works its way down, and when you're mashing randomly, standing still is actually as hard as anything else. So most of the time, it'll mash itself into a pit. But slowly, it'll not do that enough to clock squares going left and left and left till it hits the far left. And then, it'll start working its way right again, and it doesn't get any of those squares back because it was just there, and its health hasn't changed. And then it'll get to the end, and the thing will try to dump it. It will eventually successfully make the jump, which is hard but doable. Again, with 500 tries, you'll get there someday. And then it goes along its merry way. In the bad cases, we start just to the right of the little kill spot. And so Mega Man does eventually mash his way to a successful jump over to the left, grabs all those same grid squares, and then has to come all the way back to the right in one motion, where he has to make it not just all the way back to the right, not just all the way back to the right and over the little jump, but all the way back to the right, over the little jump, and then standing still long enough to catch the next square over. We've sort of cannibalized this square going the wrong direction. So we've got an exciting new non-convergence, and this, ate a week of my life several years ago. So what can we do about this? So one thing we can do if we're just trying to be more convergent in general is instead of optimizing or, as a factor to optimizing, we can have some percentage of the time just do a random replacement, right? So instead of getting stuck with some corner case that might be, badly optimized of something that we're not seeing, some percentage of the time we just swap out. That puts sort of a ceiling on how stuck we can get in a naive sense. But with a problem like this one, the confusion is already baked in several squares away. By the time this platform is loaded on screen, we're already screwed because we've already got the pattern of them side by side, right? So we can, keep replacing his landing over and over again, but he's always falling from approximately the same place. This will get us through here ever, but it still takes a super long time. What we really want to do is shoot for convergence on purpose, right? We want convergence to be our primary target. And so we want, basically the sort of function that would fit this pseudocode, which is give me an ordering where, the more convergent one wins. That's not, a natural property of the universe, but we can sort of build out what that would look like. And so, we've got 2 nodes up here. Did I talk about trees? So I think I dropped this before. When you have a deterministic input system, like something that you're fuzzing, you can think of each place that you make a choice to feed something in as a branch point in a tree, right? Everything toward the root shares a set of inputs, and then if you make a different input, you have a new child there. So picture, some set of states that we've seen in a tree like this. blue one is one that we found a little while ago. The red one is a new one. And the question is sort of like, which one of these is contributing more to having a convergent, like, exploration of the program space. To do that, right, we can sort of think about it as the, like, historical ordering of where things are coming from. So first thing we want to do is we want to find their, like, latest common ancestor. Up here I've got that marked in green. And then we want to see, you know, basically which branches from that ancestor lead to the states that we're comparing. Right, so the red ones come in red, blue ones come in blue. And what we see is that even though this red state is new, incoming, what it came from, what its parent was something that we found a while ago. And so we can ignore that and keep pursuing this blue line, which is like a new, different thing. And this puts like a pretty hard cap on how bad we can actually get, right? A policy like this, no matter what hidden state we're ignoring in our, like, favorite optimization, if we spend, you know, half our time replacing things this way, we'll always, you know, let things percolate through. So if we draw a state, in the example we were looking at, right, if we draw a state from way back over to the left, it will naturally start replacing everything to its right as it goes again. And eventually, when it, you know, makes it to the platforms and loads those in, we have another go at them. And so it might take a few tries, but it doesn't take thousands and thousands and thousands and thousands of tries. And with that, seriously, right, of course. This is super sad. This is an actual playthrough of us, like, spending half an hour beating Mega Man. I am happy to share that with people when we get to the drinking part of this, because it's pretty cool. And I was just going to let that run while we talked. So that's the talk. If you looked at that and were like, wow, that's cool, why did anybody, like, pay you to play Mega Man for a month? The QR code on the right is my CEO Will explaining with Mario why this was relevant to the business. If, you know, after listening to me talk for half an hour, you think, man, what I really want is to hear that guy talk a bunch more, maybe you should be my coworker. We've got a hiring link here. And if you think, man, I want to be part of this thing is really cool, but the California weather is gorgeous, there's no way I could possibly be dragged out of here, you should send an email to jobs@antithesis.com, because we're looking for, you know, DevRel and sales engineering and who knows what else over here now. Cool, yeah, that's the talk. If I've still got time, I'll take questions. I assume I ran long. 5 minutes? 5 questions? 5 something. Are there questions? If not, that's super easy. Carl? Yeah, exactly.
So my question, pretty cool talk. My question is, like, I'd love to be able to click on one of those drafts and immediately drop into, like, a debugging session where you just play from that point. Did you do that?
Yeah, so at the videos that some of the videos, a lot of the GIFs, a lot of the screenshots actually came from exactly, you get the way that I've got it rigged up right now, it'll give me, you know, this is how many times we got to this point, here's like a random place where we got to this point, and you can play that back forward in a new emulator and leave you at that state. And that was, you know, I spent all last week doing that to make this talk. Back there. There we go. Somebody just had to get us started. Amazing. Oh, sorry. Wait, didn't you have a mic for that? I did. Oh. Okay, great.
So I have a question about the search space and the search states that you use to define. It seems that having a more detailed search state would make the search a lot easier, but it sounds like you guys were more interested in keeping kind of a more broad, generalized state. Is there a specific reason why you went about doing that? Does that fit the work in other areas that this is supposed to extend to?
Yeah, so I think there are basically 3 different things pulling us in the direction of trying to be minimal here. First is that, you know, like, hinted at in a couple of places, if you hang on to too much stuff, you're not narrowing the search space, so you're just like, to compute all possible configurations of Mega Man is like longer than the Earth is going to live, right? And so if we want to find the winning ones, we need to narrow that space to a smaller set that, is where the winning ones are a much larger fraction. So things that don't narrow it enough aren't saving us enough compute time, aren't actually helping us get anywhere interesting. For other things, like why don't we just take like a much broader sense of stuff? We also have like, eventually you'll hit memory pressure, right? How many things do you want to hang on to? Even if you have enough compute to dispatch it, like your list gets a little bit long. And then, so the last thing is, when we are thinking about, code coming into our company, we don't have the same level of gray box access. We have coverage, we have our assertions, we have some cool ways to hook in, but we don't have like exactly this is this one variable all the time, let's keep an eye on it. And so trying to be a little bit more minimal there was a better intuition pump for the things that we want. I did it again, didn't I? The question was, why were we trying to minimize the state space that we were working through? Sorry, I'll get better at this. It's when they have a mic, I don't think about it.
Hi, great talk. One of my questions is, it seems like in this fuzzing approach, you used a lot of domain-specific information. You're like, okay, we should probably go right. We should probably not have our health go down too far. But if I just give you a concurrent program that's bugging in a very subtle and particular way, and you don't know anything about what it's doing, how do you design a fuzzer to find that? It seems like in that case you have to just try randomness.
So how do we fuzz programs where we don't have the level of domain-specific knowledge to be like, that's X and that's Y, and I want to go to all of those? So when we move back to regular programs, we actually do get to take advantage of one of the things that we didn't for Nintendo, which is code coverage, which is tremendously helpful. In a lot of languages, it's easy to hook into something like some way where you get notified every time you hit some part of the code for the first time. And you can do a sort of exploration that's exactly analogous to this grid search that I was showing, where you have buckets of, here's a bucket where I hit this cluster of edges, and here's a bucket where I hit that cluster of edges, and let's try to explore equally from all of those. And so that's not zero knowledge, but you can get a lot of value out of that. If you're stuck at actual for real black box, or like, you can't get anything in the program, the next thing you look at is other output, right? You can say, what is it doing? Is it making network calls? Is it printing log lines? And you can use those same things to feed strategies like this, right? It's a lot harder to, slice and dice, like threading problems if the only thing you have are like the output error messages. So, a lot of what we do as a company is make it easier for people to supply information rather than just getting better at working without it. But there are a few things you can do with a program that's not deliberately trying not to be read.
I had a question about how do you account for states where you glitch through something, you get to where you wanted to, but you didn't follow the path that you wanted to.
Oh man. So this was a real thing that got cut from the talk for length. That's my favorite question of the night. So there are basically two different versions of this, right? The first is where, how do we deal with state, thank you so much. How do we deal with states where we got somewhere by means of a glitch? There are basically two versions of this, which is first, where we basically got somewhere that we wanted to get and happened to use a glitch along the way. The video that I'm not showing right now actually does that a little bit. It does like a block duplication glitch to kill some guys, and that's fine. Like that's fun. It's hilarious. It makes great content. There's the world record human speed run glitches through a ceiling to pick up a weapon early. It's cool. The glitch that really gave me a hard time is one where basically you can get the sprites and the screens out of sync with each other. And so you can get to a place where basically the edge transition is on the ceiling, but the ladder didn't load. And this just is the hidden state problem. In practice, either you get good enough at trying a bunch of different things that you don't hit it, or you throw in an extra variable for have I screwed up this transition. When I actually did it, I did the second thing and then the first thing because that was the order that those got figured out. But going back, you can run it without the special knowledge of the glitch state, and it will still get through there eventually. Anybody else? We good? Up?
Yeah, so thank you for the talk. This might be a little dated, but I remember the Atari DQ and their, the game they had an issue with was Prince of Persia, which is very similar to side scroller. So just, which do you think is harder, Mega Man or Prince of Persia?
Oh man.
And then, on top of that, let's start that.
Okay, which do I think is harder, Mega Man or Prince of Persia? With this informed by the fact that we had a learning paper, trying to work on Prince of Persia. I actually haven't played the original Prince of Persia, but have it in my head as a thing that's very hard. I will say that for fuzzing as an approach, the things that make a game hard for humans and the thing that make it hard for a fuzzer are very different. So a game that's mechanically very challenging, but where there just is sort of a right path that if you notice you're making your way through, you'll make progress. Very chill for a fuzzer, even if it would be brutally, brutally hard for a human. We absolutely smoke the Mario Lost levels, for instance. A thing that I'll say, just for reading papers like that, one of the things that it's always helpful to look at is what are they doing with the input space, right? A lot of, you'll see reinforcement learning papers on Mario, but what are they actually doing with Mario? Well, they're locking the run button down, and they're only letting you press right and or jump. They have converted Mario into, and also they cut the frame rate in half. They've converted Mario into an Atari game in order to feed it into their thing. So, as a reader of papers like that, just keep an eye out for what cool tricks people are using to make the game easier than it looks. And if I'm not getting cut off, we've got somebody in the back. Oh, we're good. Awesome. Thank you guys so much. And I will on the book. I think I owe you a magnet still.
We will take 2 minutes to get the next speaker set up. Talk to your neighbor. We're not going to take a break, but you can have the lovely food after we finish the next talk.
Amazing.
Okay, thank you.
In those 2 minutes, what are you saying? A lot of you asked me how much work this was to set up, and the answer is, for me, it was none, because Caroline did so much.
No, we have your slides.
Yeah. Did you share them with us? We did. B. Eggers? Oh yeah, there they are.
Okay, let's get you set up on the mic. Will? No, Will?